Uh, for multiple cash flow, if we do it one by one, of course we can still do it, but it's very tedious. In some cases, with the special pattern that the cash flows have, we can easily convert them into a single value or convert it into something different just by knowing their periods. For example, we are looking at these 5 cases, and we will go through them one by one. They may be of equal payment, right? The uniform series. There could be linear gradient going up or coming down. They could be geometric gradient series. That is the increase is exponentially. So these are some of these patterns can be converted rather efficiently if we know how to do it. Again, previously we have sort of shown this already. Now it also comes to the point where we want to use a symbol to represent it. Here we have a very similar case where we have payment at the present time, and we want to know its future worth so that we can repay it. We can obtain it. So from present to future, we have seen this. That is, we will use p as a present value times 1 plus a to the nth power. Okay, and that will give us f. But then we don't need to write explicitly on this equation, because what the equation means is once we have I, we have n, we can compute the value. It's just a single value. But if we have already pre-computed such values, we can look them up on the table. So instead of using 1 plus I to the nth power, we can say we want to find a future value which is equal to the present value times symbol, which is given p phi f, given present value phi future value, comma interest rate, comma number of periods. Okay, so the symbol below represent the equation up there, the formula up there. Okay, so we can compute still. We can compute the value directly and use p times that value, or we have p and we look it up on the table. We look at I, we look at n, then we'll get this coefficient, and we can use p times that coefficient. It will come to the same f value. Okay, so again, here we are saying that we are given something that we want to find, another thing, and this something need to multiply by a coefficient. That coefficient can be calculated directly based on the concept of time value of money, or based on the accumulation of the interest with the principal, or we can just look it out from the table behind most of the engineering economics book. Okay, so in this particular case, if we are looking at 10% interest rate, period of 8 years, and the present value is 2,000, we want to find future value. So future value equals present value times 1 plus 10% to the 8th power. We can write it this way, and we can compute, which will give us 4,287.18. But we can represent that formula by this symbol, that is still given f, given p find f, comma 10% and 8 years. And we look it up from the back of the appendix of the textbook. We can come up with a value which is probably 2 point something, and when we multiply them, it will also come to 4,287.18. So the two will give us the same future value. And reversely, if we are at the future, we want to know its present value. Okay. So rather than given given p find f, now we have given f find p. And we can just take the equation from the previous slide and move it to the other side. So now we have p equal to f times 1 plus I to the minus nth power. And we can also read this as the present value equals the future value times the symbol where we have given f, find p, comma, interest rate I, comma, and period n. So that again can be looked up from the appendix of most of the engineering economic book. So we look at the example, assuming that we are looking at interest rate 12% and time period 5 years, and we have a future value of 1,000. We are trying to find its current value, its present value. So we can take the future value 1,000 times 1 plus 12% to the minus 5 power, and if we compute the coefficient, then we can get a certain value. But we can also represent it by a symbol. Again, it's 1,000 times p given f by p, comma 12%, comma period 5. So if we look it up from the back of the textbook, again, that particular coefficient can now be obtained directly and use it to multiply 1,000, and we will still get 567.4. Right? The value should be smaller than 1,000 because they are the equivalence. Okay. And if we have uneven payment, big and small payment, if we have uneven payment, we can also do the conversion and one by one, and then reaching the same results. Right. So it's just similar to the previous one. We can put these kinds of conversion into something practical that we face quite often, and we can appreciate the conversion. For example, you are getting a long-term contract. The contract include some contract salaries. So you can see that there's a column of value. At the present time, it's 21 million, and it goes for a few years, and it becomes 25, it becomes 27, and you will have prorated signing bonus. It will be distributed to 5 equal payments between now and the end of the 4th year. So if we add them together, they will give us a combined cash flow that you can see here. So then in the beginning, for the 4 periods, we'll get 23 million and 27 and 25, then the rest of them 27. Okay, so these are numbers that we see. But if we see this, we saw the number, but we can't really feel the true value of these number. That is because the first payment will be right now. So that 23 million you feel and you know how much it worth. But then the second 23 million, which comes 1 year afterwards. So 1 year from now, 23 million, can it buy the same value of the products? Can it still be enough for paying salary or buying materials from suppliers and so on? So we are not very sure 23 million in the future how much it worth. Okay, and we want to know, in fact we want to know for the entire contract. It's a long-term contract. For the entire contract, what is the actual worth that we are getting? I want to look at these numbers at the present time and knowing its value. So that requires the conversion we just described in the previous few slides. We take all of these cash flow, we convert them one by one to the present time. So the first one is 23 million. The second one will be given F5P and still use a fixed interest rate, which is 6%, and it should be moved 1 year or 1 period earlier. So you get 1 here. And then the next one will be again given F5P and 2 periods and so on. So every one of them can be converted from the future to the present time, and adding them together to get 212.75 million. So that number gives us how much it worth, how much the project, the long-term project, long-term contract worth at the present time. So it's a lot easier for us to conceptualize how much it worth. Okay, it's easier to see them in the current money, so that we can compare with what we can do, what we can buy, and so on, so that we know that is the actual value. So that's a very simple but very useful example. We just convert them into at the same time point, but then I think most of the time we'll convert it to the future, to the end of the entire contract, or to the present time, so that we can really have a feel of the actual worth of the cash flow. But sometimes, or in fact quite often, that we have cash flow of equal payment. When we have that, in fact, there's an easy way to get the result. We don't have to convert them one by one. If we have n equal to 240, then we need to multiply that many times, which is not very fun. But then if we have equal payment, then we can just utilize some formula, or using the kind of symbol I introduced previously, to look up from the the tables in the appendix so that we can utilize the number directly. So here is one example. We have a series of payment over n periods. We want to know its future worth. Okay, so if we derive them, well, it's not too difficult that we can come out with the formula in the box here. Then we can plug in I, plug in n, then we can still compute the value and multiply by a, then we can get the future value. But we can also consider the symbol that we introduced previously. That is, we assume that we know a, so given a, we want to find its future value. We want to find f, and with the interest rate I and n period. Again, you go to the back of the textbook and you find the column where it given a, find f. Then you go to the page where I equal to a certain percent, and and on that page you look at n, then you can find the coefficient and can just jot it down here, and you multiply them, it will come to the same result. Okay, so here if the equal payment is 3,000 for 10 years and the interest rate is 7%, we are given a, we want to find f, and we can go directly to the back of textbook, go to the page of 7%, and look at the column of given a, find f, and then go down to n equal 10, then you get this coefficient, and multiply by 3,000, you will get 41,449.20. So given a, we can find f. With this kind of equal payment series, it's quite easy to compute future value. Similarly, if we are given f, we can also compute the equal payment. Okay, compute a. So if we take the equation from the previous slide, and we just need to move the coefficient from one side to the other side, and swap them from the above the equal sign. So instead of given a, find f, now we have given f, find a, and f need to multiply a coefficient which can be computed from the formula, but we can also look up the number from the appendix. Again, you go to the page where I equals to a certain value, then find the column with given f, find a, and go down the column and look at the value where n is the period that we have, and you can get the value directly and use f to multiply that value to get the equal payment a. So if we look at the example, we are given, let's just say f equal to 5,000 and n equal to 5 years, I still equal to 7%. We are given f, we want to find a, so the solution will be a equal to A equals 5,000 times this symbol, given F find A 7%, 5 years, and we can look it up and find the coefficient and multiply by 5,000 and get 869.5. Okay, so that's given A, find F, which is quite intuitive. We have a lot of payment, we want to know its future value. Or given F, we want to compute what will be a series of equal payment that we can do. Okay. And we can not only do it for future value, we can also do it for present value. Okay, and it will be just the same. Instead of given F, find A, now we have given P, find A, and because we know the relationship between P and F, right? So we can take the formula from the previous page and multiply by the relationship between P and F. Then we get that formula, a new formula. Again, plug in I and plug in N, we can compute the value, and we can just use the value. Or instead, we look it up from the appendix on the page of I, and on the column of given P find A, and go down the column to the right end. Then take the number and use it to multiply the present value. Then we can have present value, and we'll compute the equal payment A. So there's also an example there. Given P equal to 250,000 and N equal to 6 and I equals to 8%. We want to find A, and solution will be 250,000 times the coefficient, which comes to 54,075 for the 6-year period. Every time you pay this amount. And instead of given P find A, we can also given A find P. Okay, given A find P, again, it will be taking the equation from the previous page and take this coefficient to the other side. Okay, so which will be an inverse. And we can again easily plug in I and N and compute for the coefficient, or look it up from the appendix for the value, and it will be very straightforward. Just use the value times A, then you get P.